Hi, we are Group 0 of ECE 2031 L11, aka 27 Raccoons in a Trenchcoat. In this video, we're going to demonstrate the hardware peripheral that we've created to allow SCOMP to easily communicate with the LTC2308 analog to digital converter of the DE10. First, we're going to briefly explain how we've designed the peripheral to be used. Then we're going to give a couple live demonstrations of the peripheral in action. And lastly, we'll conclude with a summary of why we believe our implementation is one of the strongest choices for an LTC2308 hardware peripheral.
So to start, we've designed the peripheral to be as easy to use as possible, which in this case means that there is only one address that the user needs to be read from and write to. The address is 0xC0. The peripheral is implemented using VHDL and is located just on the D10's FPGA chip. Writing to the peripheral configures the ADC, and we maximize the amount of features available. The user is able to set which pin or pins to read from, whether to read in single-ended or differential mode, and what the sampling rate should be. They can also set the peripheral to sleep to reduce current consumptions. Reading from the peripheral gets the 12 bits of data from the ADC given the most recent settings, along with some other flags. The old data flag is high if the user has already read the most recent sample from the ADC with the previous in instructions. We've implemented these features because SCOMP runs at much higher frequency than the ADC, meaning multiple in instructions can occur for one reading. So we found it useful for there to be a way to distinguish between getting the same data from the same reading versus different readings. The wave flag is high if the peripheral is in the process of sending settings to the ADC, whether that be because it was previously in sleep or if the user just sent new settings. If either of these flags is high, then the data should probably be discarded. We created a simple way for any user to do this by making the most significant bit of the output data as the OR of the two flags previously explained, so that a JPOS JNEG SCOMP assembly instruction can easily distinguish between good and garbage data. A detail to note is that the peripheral initialized the ADC to sleep upon reset. Since we recognize that most applications of SCOMP are unlikely to use the LTC2308, so we don't want to waste power when we don't need to. Or the user needs to do though to start sampling is to send one out instruction with their desired settings. From then on, the peripheral will keep on getting data from the LTC2308 with the desired settings, and the user is able to get the most up-to-date data at any time with an in instruction. Here's the register map with a mapping of what each bit signifies. The read row is the format that the peripheral output with an SCOMP in instruction, while the write row is the format data should be in with the SCOMP out instruction. Here's a table showing what the values of pin input correspond to. And here's a table showing what the values of sampling rate correspond to. Note that the max sampling rate is 500 kilosamples per second because that is the max frequency the LTC2308 can physically acquire data at. Now, we're going to move to the live demonstration of the hardware peripheral and ADC.
Our first application demonstrates the peripheral simply getting data. The input to the ADC is wired up to a potentiometer so that turning the dial adjusts the input voltage to the ADC pin. As you can see, the data displayed correctly responds to the changes in resistance. The peripheral returns data in binary format, with one bit representing 1 millivolt. This is displayed as a hexadecimal value on the display. However, for the sake of clarity, we can also convert the hexadecimal value to decimal in software for easier visualization. As you can see, the maximum voltage is 4095 millivolts, and the minimum voltage is 0 millivolts. Now we're going to demonstrate the ability to switch between input channels for the ADC. The right potentiometer is wired to a different input pin, and in this case, flipping the rightmost switch switches to that pin. As you can see, the data still correctly responds to turning the right potentiometer too. Now, we're going to compare the data the peripheral returns with the actual voltage to verify correctness. We do this through an oscilloscope that is connected to the same node. As you can see, increases in the voltage measured by the peripheral correspond with increases in voltage measured by the oscilloscope. and same for decreases in voltage. Our second application presents the bit flags that the peripheral sets, as well as demonstrating the peripheral's sleep functionality. As you can see, the value displayed alternates between ignoring and responding to changes in the input voltage, and the reason for this is because we alternate between sleep mode and acquiring data every 3 seconds. When the peripheral is acquiring data, the peripheral's output is filtered in software so that only unique readings are displayed, resulting in the top digit of the hex display being 0, since all the displayed data is valid and newly acquired, so no flags are set. Then, when the peripheral is in sleep mode, the old data and wait flags along with the data valid flag get set, which is why you see this E value in the top digit, since that corresponds with the binary value of 1110. The lower 12 bits are the data from the most recent reading before the ADC was put to sleep. Normally, the ADC itself would not be able to output data while sleeping, but through our peripheral, SCOMP is still able to get responses within instructions. Considering the complexity of direct ADC interactions through SPI, the behind-the-scenes management that the peripheral does greatly simplifies the work that the SCOMP user must do to put the ADC to sleep.
Now, just getting data is all well and good, but we recognize that potential users want some more complex and realistic applications for our peripheral. So, we've created a simple game that we call Vault Cracker to demonstrate one possible use case for the ADC. Here, SCOMP generates 2 random numbers at the start of each round. Like before, 2 of the ADC input pins are connected to 2 potentiometers. The player must adjust the potentiometers such that the ADC readings match the random numbers within a margin of error. The flashing rate of the LEDs indicate how close the player currently is, with a higher frequency indicating the player is getting closer. The number of deciseconds it took the player to correctly adjust both potentiometers is displayed on the hex display. The SCOMP program is able to get up-to-date data for both potentiometers by constantly switching the ADC configuration settings.
So to summarize, the design of our peripheral emphasizes simplicity while also containing an ample set of features for SCOMP users to take advantage of. Essentially everything the LTC208 can physically do on the D10 is made available, from different pin inputs to the sleep mode. But we've made the interface to do so extremely intuitive by having all communication done through one read and write register. We hope to have made all these strengths obvious through our demonstrations in this video. Thanks for watching.